Good morning. This talk is about rVMI, a tool that allows you to perform full system analysis. Before we get into the details of rVMI, let me provide you with an overview of the talk today. So first of all, we're going to introduce ourselves. Next, we want to talk about the motivation behind rVMI. So what is rVMI actually, and why is it interesting? Why should you care about it? This will lead us to a more detailed discussion of rVMI itself. In particular, we want to present the architecture behind rVMI and also discuss the current open source implementation of rVMI that we will make available to the community after the presentation. Having described rVMI in theory, we of course also want to show you the tool in action. For this purpose, we prepared a live demonstration that gives you a good overview over the features that rVMI provides. And finally, we will conclude the talk with a short summary. So who are we? Essentially, the rVMI project started as many other German projects do, with a couple of German engineers in a beer cellar.
So I'm Jonas, this is Sebastian. In addition to being German engineers, we're also engineers at FireEye. We've been working on malware detection there for about the past 3 years. But even before our time with FireEye, Sebastian and I have been working together for quite some time, so our research interests align quite a bit. We both have a very strong background in virtualization and virtual machine introspection, or VMI. Also on the security side of things, malware analysis, novel exploitation techniques, things of that nature. And while it is certainly true that German engineers are generally motivated by one thing, in this case there are 4 things that motivated us with respect to rVMI. Before we get into those, though, I want to give you the quick sort of tagline, the quick elevator pitch with respect to what rVMI is. So rVMI is really a debugger on steroids. If you think about how it behaves, how you interact with it, the kind of features you would expect, it really is a debugger for an entire operating system with a focus on malware analysis.
So with this tagline in mind, let's take a closer look at the 4 points of motivation that Jonas just mentioned. First and foremost, rVMI runs completely isolated from the target system in contrast to traditional debugger, and we achieve this through virtualization. In spite of this isolation, the analyst has still full control over the virtual machine through virtual machine introspection, allowing her to pause and resume the virtual machine at any point in time and to use traditional debugging functionality such as breakpoints and watch points. In addition, the analyst can access the entire state of the virtual machine while performing her analysis and can even access kernel data structures, which we achieve by combining memory forensics with virtual machine introspection. And last but not least, we provide an interactive and scriptable interface that really makes it easy to analyze the malware and to automate tasks. So with these points of motivation in mind, we hope that you get a little bit excited about rVMI, but you may still ponder the question, why did you actually do it? Why is it interesting? Jonas and I firmly believe that malware dynamic analysis is an important technique. It essentially allows you to execute a sophisticated malware sample or a sophisticated exploit in a controlled environment and to observe its behavior. And that's really very important when you try to gain a full understanding of a sample. If you want to perform manual dynamic analysis today, there are essentially 2 tools that you can use: debuggers and sandboxes. And while both of them are really valuable, they have certain drawbacks when it comes to interactive dynamic analysis that we want to discuss.
So if we start with debuggers, especially if we consider sort of the de facto standard debuggers, things like GDB and WinDebug, they certainly are very sophisticated pieces of software, and they do very well what they were designed to do. The problem is they weren't designed for malware analysis. And we see that, for example, they share the same environment as the sample being analyzed. They use operating systems APIs to perform their functionality. And there's even APIs and mechanisms that allow a process to determine whether it's being debugged. So all of that make it very difficult for a debugger to hide its presence. In addition to that, if we sort of consider more sophisticated malware or more sophisticated exploitation flows, we generally aren't talking about a single process. We're talking about a process that spawns another process or injects code into another process, or in some cases even manages to get code running inside of the kernel. And in a situation like that, it becomes a little bit cumbersome to use standard debuggers. You have to maintain multiple sessions. It's difficult to share state between those sessions, things of that nature. On the other hand, if we look at sandboxes, in sandboxes we really trade this interactive nature for isolation and invasion resistance. So sandboxes really focus on providing an environment in which it's difficult for the sample to determine that it's being analyzed. However, if you consider the way that you use or interact with a sandbox, you generally submit a sample, you let it run, you get some kind of report you can parse or analyze. And there might be some limited configuration, the type of events you're interested in, the amount of data you're interested in, but it's certainly not something we would call an interactive experience.
So if we take into consideration what Jonas just described, it should become quite clear that neither debuggers nor sandboxes were designed for interactive dynamic analysis. Essentially, we face a trade-off between visibility and flexibility that debuggers provide and the isolation and evasion resistance that sandboxes provide. As an analyst, however, I actually would like to have a tool that combines all of these properties. And since Jonas and I were not aware of any such tool, we created rVMI, which was particularly designed for the purpose of interactive dynamic analysis. So with this motivation in mind, let's take a closer look at the architecture behind rVMI, because if you want to brew up something fresh and cool, the architecture is really crucial.
And this is where I'd like to mention that while we're going to go over sort of the formal architecture here, this wasn't a project that was born out of architecture or born out of the architecture. It was something that was really sort of a evolution. So both Sebastian and I were engineers, we're hackers. When the tools that we use don't do what we want them to do, we fix it. So while Sebastian will go over sort of the formal architecture, I'm going to try to tell the story a bit of how rVMI came to be.
Let's begin by taking a look at the goals that we actually try to address with this architecture. And these goals are essentially directly derived from the motivation that we just presented to you. So first of all, we want to have a better evasion resistance compared to a traditional debugger. The malware shouldn't be able to attack the debugger directly. In fact, it shouldn't even be able to see that it's being debugged. In addition, we want to have the ability to perform full system analysis. This means we want to be able to analyze user space processes, kernel driver, or even pre-boot environments all in a single tool. And last but not least, we want to keep the interactive and scriptable nature of debuggers such that we can steer the analysis easily as an analyst and automate tasks while performing the analysis. With this goals in mind, let's take a closer look at the architecture and how we address each of these goals, starting with our first goal, resistant to evasion.
So we started probably where most analysts start. We have our analysis VM. We have a bunch of tools preloaded in the analysis VM. We load our sample, we let it run, and we start our dynamic analysis. So this grants us some isolation. We are sure that our host won't get infected. We can also take advantage of things like snapshotting that most hypervisors provide. And this is really very much the starting point.
So the first building block in the architecture is virtualization. As Jonas just said, virtualization is generally used to isolate the host system from the malware running within the virtual machine. In the case of rVMI, we take this concept a step further and pull the debugger out of the virtual machine onto the hypervisor level, such that the malware is no longer able to attack the debugger directly and isn't even able to see the debugger. And this really increases the evasion resistance of the entire approach. With this in mind, let's take a look at our second goal, full system analysis.
So eventually we started to see some of the limitations that we talked about during our motivation. And we kind of fell back or leveraged our background in virtualization and VMI. And effectively what we started doing was we started hacking the hypervisor to augment our analysis. So some of the things that were a little bit more difficult to do within the guest, we just started doing outside of the guest. And in the beginning it was very basic, it was very rudimentary. We would do things like hard code offsets. The output came out through syslog. So it was really very basic, very rudimentary, but this is really the beginnings of rVMI.
If we pull the debugger out of the virtual machine, we still need some means to actually control the virtual machine from the outside and to inspect the virtual machine from the outside. And these are exactly the two capabilities that our second building block, the VMI layer or virtual machine introspection layer, provides. It allows the analyst to control the virtual machine, meaning to pause and resume the virtual machine at any point in time, and to inspect the virtual machine. So take a closer look at the registers of the virtual CPU or the physical memory of the virtual machine. And this functionality is exported through an interface such that we can actually leverage it as an analyst. While this already seems to address our goal of full system analysis, there's a problem that's closely related to VMI that we haven't discussed yet. And this is the so-called semantic gap problem. So essentially, while VMI allows us to see the entire state of the virtual machine, our view of that state is very different than the view that the guest operating system has. As an analyst, essentially, we just see the bits and bytes in memory from the hypervisor, but we don't have the semantic knowledge that the guest operating system has that would allow us to interpret this view. So we don't know where the guest operating system placed its structures in memory and how these structures actually look like. So while this example here looks random to us, the guest operating system might know I placed an eProcess structure at this particular location, and I also know the fields in this eProcess structure, so I can interpret this view and interpret these bits and bytes. If we want to create a tool that's really helpful for full system analysis, we also need to provide a similar view than the guest operating system has in our debugger, such that we can leverage the kernel data structures while performing our analysis. And this is why we introduced a third layer into our architecture, the semantic layer.
So at some point we got kind of sick of constantly hacking the hypervisor, updating the offsets, and we also realized that the memory forensics tools that are out there, they really solve this semantic gap issue that Sebastian just talked about very nicely. So we decided to leverage them, and we started by instrumenting the virtual machine to generate guest physical memory dumps at the point in time that we were interested in, and we would feed those into the memory forensics tools. And this would give us a nice holistic view of the operating system at that point in time. So we could look at any process, any kernel data structures, things of that nature. However, we still had to instrument the hypervisor with respect to exactly when and for which events we wanted to generate these guest physical memory dumps.
The third building block in the architecture is the semantic layer. And as the name suggests, the purpose of the semantic layer is to bridge the semantic gap and to reconstruct the knowledge that the guest operating system has on the hypervisor level. In addition, it needs to export the semantic knowledge similar to the VMI layer through an interface such that we can actually use it as an analyst while performing the analysis. This leads us to our last goal, an interactive and scriptable interface.
So finally we realized we actually didn't need to generate an entire guest physical memory dump each time. And we simply plugged the two components together. And we did that by exposing the guest physical memory directly through the VM. And then analyzed it directly with the memory forensics tool. So this allowed us to simply start and stop the VM and then directly perform our analysis without having to generate a guest physical memory dump. And over time, we added control commands that enabled our interactive interface. And also at this point, we effectively stopped using any of the tools inside of the guest. So all of our analysis really was done outside of the guest.
The last building block in our architecture is the interactive interface. And this is really where everything comes together. It is the environment in which the actual analysis is performed. And to accomplish this, the interactive interface makes the capabilities that the VMI layer provides and the semantic layer provides available to the analyst through a single interface, such that we can actually use them. In addition, it provides support for scripting, such that we can automate tasks while performing the actual analysis. Having described the architecture behind rVMI in theory, we want to take a closer look at what we can actually get out of this architecture. For this purpose, we want to discuss the current open source implementation of rVMI and describe how we implemented these building blocks that we just described in theory in practice. Starting with our first building block, the virtualization layer.
So for our virtualization component, we went with QEMU KVM. It's actively developed, it's well maintained, it's also easy to install and use. So for us, it was really the natural choice. But that said, there's really no dependency per se on QEMU KVM. All the changes that we made, you could apply to any other hypervisor that supports hardware virtualization, and then simply plug the rest of the system into that. So in the next slide, we'll look at some of those changes in the form of the VMI component.
To implement the VMI component, we essentially extended KVM and QEMU to provide VMI functionality. And we tried to keep this VMI layer as simple as possible to make rVMI portable to other hypervisors as well. Essentially, the VMI layer exports the functionality that modern Intel CPUs provides to an analyst such that she can use it to perform VMI. And this functionality is exported through an interface referred to as QMP. QMP stands for QEMU Machine Protocol. It's essentially a JSON-based protocol that was designed to control QEMU instances through a socket connection. And it just seemed like a natural place to also implement our VMI commands. So this means an analyst can now essentially send JSON-based VMI commands to our VMI layer, which will interpret them and execute them. At this point also then a word of warning, since we rely heavily on the features that modern Intel CPUs provide, the current implementation is restricted to Intel CPUs only. We will see some of these features that we use later on in the live demonstration. But for now, let's move on and take a look at the third building block, the semantic layer.
So in the last section, I talked about a memory forensics tool. Specifically, we rely very heavily on Rekall. Rekall is a very powerful memory forensics tool. It's written completely in Python. And it has a very pluggable architecture. So through that, it really supports all of the major operating systems one might expect: Windows, OS X, and Linux. And it also has all the features one would expect from a memory forensics tool: enumerating processes, listing loaded drivers, inspecting data structures, things of that nature. And effectively what we did was we leveraged this pluggable nature and began writing plugins. So the first plugin we wrote was the interface with the guest physical memory, so that the Rekall could directly access the guest physical memory. And then over time, we added these control commands that then fed into the interface component that we'll have a look at now.
Rekall already provides an interactive interface in the form of an IPython shell. And we decided to extend the shell with VMI commands to make the VMI functionality and the Rekall functionality available through a single interface. So essentially, we implemented Rekall plugins for all the VMI commands that we support and made these available through the IPython shell, and also created a Python API that would allow scripting and using these commands within scripts. In addition, we added VMI events. So essentially, whenever something interesting happens within the virtual machine, for instance, a breakpoint is hit, a VMI event will be generated and will be sent in a JSON format through the QMP socket through the rVMI Rekall layer. And this Rekall layer will then make the event available through the IPython shell for manual analysis, or through the Python API in case you want to perform scripts based on certain events. Having described the architecture and the implementation of rVMI, we hope we got you a little bit excited about the system, and we of course also want to give you a taste of the whole tool. For this purpose, we prepared a live demonstration that will give you an overview of some of the features that rVMI provides, and in the following we'll move into this live demonstration.
So while Sebastian's switching over, I'll give you a little bit of an overview of what you're going to see. So we have a WannaCry sample. You guys are probably familiar, if not in detail, at least by reputation. And specifically, we're going to look at the propagation mechanism. It's sort of one of the more interesting parts of WannaCry. So for that, we actually have two VMs set up, a host VM and a target VM. The host VM will infect the target VM, so most of the interesting analysis that you're going to see will happen on the target VM.
So what you see here is the rVMI interface. It's essentially an interactive shell that we can use to analyze the system. Please let me know if you cannot read this. I can enlarge the font a little bit. So essentially, this interface is where we perform the actual analysis. And every time we see the shell prompt, it means the virtual machine is paused because we're performing our analysis. If I would go to the target machine now, you see I cannot move the mouse, I cannot interact with the virtual machine because it's currently paused. Of course, we can also resume the virtual machine, and for this purpose, we want to take a look at our first command today, the first rVMI command. Essentially, this shell supports tab completion, and the first command that we want to use is this continue command, which will resume the execution of the virtual machine. You see the prompt goes away, and now if we go back to the target machine, we can actually interact. I already opened the start menu here, I can close Windows, and etc. If I go back to the interface now, I of course can also pause the virtual machine at any point in time. I can do that by simply pressing Ctrl+C, and then we get our prompt back and can analyze again. So you see there's some information printed to the screen. First of all, the event that occurred is printed. These are the VMI events that I just referred to in the implementation, and we see on which CPU this event occurred in. Since this was a user-triggered event, I press Ctrl+C, the CPU is set to none, so it didn't occur on any of the CPUs. We also see the current context. So essentially, this virtual machine that we're looking at has two virtual CPUs. We see the current instruction pointer on each of those CPUs. We see the PID in context, the TID in context, and the DTB of the process in context. So with this short introduction to the rVMI interface, we will now take a closer look at WannaCry and how we can analyze it using rVMI.
So the first thing that Sebastian is going to do is he's going to enable the LBR, and I'll talk to that in just a moment. He's also going to set our first breakpoint on EXAllocate pool, and he's going to do so using the symbol name. So Rekall will resolve that for us. Of course, if you want to set a breakpoint on a virtual address directly, you can do that as well. And we'll give Sebastian just a moment here to get all the VMs started and WannaCry started so we can have a look at the propagation. And while we wait for the breakpoint to hit, I'll talk a little bit more to the breakpoint command. So he set this breakpoint globally, and you see he set the globally flag to true. So that is, he set the breakpoint not specific to a particular process. We want to see all execution flows that hit this breakpoint. It makes sense because it's a kernel function that we want to see here. So the breakpoint has hit. We see the breakpoint, a software breakpoint came in on CPU 0. And the first thing that Sebastian's going to do is go ahead and query the LBR. Excuse me. Now the LBR is the last branch record. This is a feature of the hardware that effectively will show you the control flow leading up to the current point in execution. This particular CPU here has 16 such records. Each record is comprised of a from and a to address. And then we have a little bit more information. So Rekall will try to resolve any symbols at that address. If you can't resolve the symbol, we get these question marks that you see here. And of course, the instruction at that address. So if we consider the first pair here, that's the most recent is always at the top of the stack. We see that it's a call to EXAllocate pool, which makes sense. That's where we set our breakpoint. But it's actually coming from a region in memory for which Rekall can't resolve any symbols. So that's, especially in the kernel, it's somewhat unusual. At least makes sense to have a closer look at this code in memory. And see what it's doing.
So a common functionality that we know from traditional debuggers is to disassemble instructions. And of course we can also do that in rVMI, and for this purpose we use the Rekall disassemble plugin. Essentially it just gets the address that you want to disassemble and the number of instructions that you want to disassemble, so 10 in that particular example. And then it will display the instructions at that memory location. Of course, you could now also take a closer look at the instructions before the call, or even dump the entire page to disk and load it up in IDA to analyze these instructions further. But for the purpose of this demonstration, we want to move on a little bit and take a closer look what else is going on this virtual machine. So let me continue here. And we see that the breakpoint is hit again. So let's get the LBR and see where we actually are. And this picture looks very different now. If you take a closer look at these function names, it seems a little bit like we are in some form of interrupt handler, and it's just something to keep in mind that when you analyze malware and you place a breakpoint globally in the kernel, it might very well be that you get a benign call to that function, as it seems to be in that case. So that's not that interesting. Let's continue again. We hit the breakpoint again. Let's take another look at the LBR. And now the picture looks very different again. So in this particular case, we're back on the page that Jonas found at the very beginning. And we want to take a closer look what's going on at this particular point in time.
So we'll have a look at the disassembly. And the first thing you'll see is the actual call to EXAllocate pool there at the very top. Now EXAllocate pool effectively returns a pointer to a newly allocated buffer. So if we sort of follow that return value a little bit, we see that it's copied around a bit, first into R9, then into RDI. We also see a few instructions later that he actually loads a RIP relative address into RSI. Since it's a RIP relative address and it's still on the same page, we might make the assumption that it's some code. And even further down, you see he actually starts copying. So he starts copying from this RIP relative address into the newly allocated buffer.
So at this point, our theory essentially is that he's copying instructions into this newly allocated buffer. And to verify the theory, we want to place a breakpoint on the actual copy instruction and take a closer look at what is happening at this particular point. Again, because we're in a kernel, I will set this breakpoint globally, and this time we use an address to set this breakpoint instead of a symbol. We can also list the breakpoints that we have currently set with this VM debug list command, and of course we can also remove breakpoints. So for this example, we want to remove the first breakpoint, which was an X-allocate pool, since we don't need it anymore, and we can simply do that by specifying the index of the breakpoint that we want to remove. Now let's continue this execution. We hit the breakpoint instantly, and at this point in time, we might want to take a closer look at the actual register state of the CPU. And to do that, we can use the VM CPU state command. So this will show us all the registers of CPU 0, and you see RSI is indeed pointing to the page that we have been analyzing so far, as Jonas argued, and RDI now points to the newly allocated buffer. So an interesting question that we may have now is to take a closer look how these instructions are copied. So for this purpose, I can first verify that RSI is actually pointing to instructions. And to do that, I can use the disassemble plugin again, and I can use this $ syntax to refer to the current value of RSI that you might know from GDB, for instance. And if you take a look here, it really seems like these are valid instructions. It even seems like a function prologue of some sort. So at this point, we want to use the scripting functionality to observe the copying a little bit. So the first thing we're going to do is we're going to save the value of RDI in this variable here. This is essentially an IPython shell, so we can use arbitrary Python commands. And for the purpose of this demonstration, we just want to write a small loop that will essentially perform a single-step operation in each loop iteration, which means exactly one instruction will be executed in the guest system. We then will use the dump plugin of Rekall to show the contents of the buffer, and that will show us how the buffer is changing. We also have to give it the number of bytes that we want to display, similar to the disassemble plugin, and we will add a new line just to make the output a little bit more pretty. So if you execute this, you nicely see how byte by byte is copied into the buffer. So exactly what you're seeing is, first of all, this single step event is emitted every time the single step comes back. Afterwards, we see the current context like for any other event. And here is the output finally of our dump command that we had in the loop and the new line at the very end. So if you take a look at these bytes, you see that byte by byte is copied into this buffer, and we can really see that these instructions are now located in the buffer. So while this was a toy example, we hope you get an idea what you can use the scripting feature for and the possibilities that it provides. At this point, we may have the question, when is this newly allocated buffer that seems to contain its instructions now actually going to be called? And to figure that out, we'll place a breakpoint on this buffer, and we'll then continue the execution.
So,
sorry, I mistyped.
Yeah, so at this point, a little bit of background. So at this point, a backdoor has been installed or is being installed. And in order for us to now see the breakpoint, Sebastian's going to go ahead and start the host as well. You see that as he starts the host, we get that breakpoint. And at this point now, if we check the LBR, we'll see that the control flow comes through this srv-sys driver. So this is the SMB driver. For those of you that are familiar with WannaCry, it's probably not a surprise. So if we were doing a full analysis, obviously we would try to understand this backdoor and take a closer look at it. But for the purposes of our demonstration here, we're just going to observe that the control flow is coming through the SMB driver. And just point out another feature of Rekall, or another Rekall plugin, the modules plugin. We can at least verify that this SRV driver is in fact loaded at the address that's indicated by the LBR. So with that, we're actually going to move out of kernel space a little bit and move into user space and watch the propagation as it enters user space.
So one of the nice features of rVMI is that you can perform full system analysis, meaning you can watch the kernel and you can also watch user space processes. And at this point in time, we want to take a closer look at the actions that the malware is performing in user space. And for this purpose, I just placed a breakpoint on anti-create user process, which is essentially the function on Windows 7 that's called when a new process is created. And since we don't interact with the virtual machine, process creations are interesting because there's a high chance that these are actually caused by the malware. So let's remove the breakpoints that we don't need anymore at this point in time. This is the breakpoint that we placed on the buffer, the backdoor that Jonas just described, and let's continue the execution. We'll also continue to host at this point, and we'll see that the breakpoint is coming back. And at this point, we might be interested which process is actually calling anti-create user process. And to figure this out, we can again use the CPU state. But as you may have noticed, this is the first time actually that we get an event back on CPU 1 rather than CPU 0. So far we always operate on CPU 0. And if you want to have the CPU state of CPU 1, we can simply pass this one argument here, and we'll get the CPU state of CPU 1 displayed. At the very bottom of the CPU state, we always print the process that's in context, and the name of the process is currently in context. And it seems like that the LSAS process is trying to create a new process.
Before we look at what process is actually being created here, we'll have a closer look at LSAS. So if LSAS is in fact creating malicious processes, we don't know that it is yet, but it's worth checking. We want to take a closer look at the LSAS address space. So we're going to do that by querying the VAD table for the LSAS process. And this is effectively a table that will show you all the allocated memory sections for a given address space. In this case, it's the LSAS process. So you see all of the DLLs that are loaded. You also see the LSAS binary image itself. And what jumps out a little bit are these two sections in memory. The reason these are interesting is because they're both allocated read, write, execute, and they don't have a file on the file system backing them. So it might be a good place to start for our analysis. We'll have a closer look at one of those memory sections. So we'll see it's just a zeroed out buffer. In fact, we have to be a little bit careful. Now that we're in user space, we actually have to specify the address space that we're interested in. So with the cc command, Sebastian is effectively instructing Rekall to change context to a process with PID 496. And if he dumps the same buffer again, hopefully we'll see some data this time. In fact, we do. And what probably jumps out here is this MZ header. So we might make the assumption this is a PE image. At least we want to verify it. We can try to verify that with the PE info plugin, see if Rekall can actually parse a valid PE header here. And in fact, it seems like he's able to, so we have some interesting information here. We see it's a library image, it's a DLL, it has an entry point, it has a text section, so there's probably some code here. Now, if we were doing a full analysis, this would clearly be a very interesting candidate for further analysis, as would the other section that we found in the VAD table. But at this point, we will simply continue.
Before we move on, I want to show you just another plugin. Essentially, you can use tab completion for any command here in the shell. And an interesting command is pedump, which allows you to save a file that you found in memory to disk and then load it up in IDA, for instance. Rekall also provides an interactive help, so you can essentially add a question mark after any command that you're interested in. You will get an interactive help that will allow you to take a closer look at the arguments for the various plugins and how to use it. At this point, we may actually be interested in getting to know which process is about to be created by this anti-create user process call. And to do that, we can take a closer look at the arguments that have been passed to the anti-create user process function. So I will just get a couple of bytes from the stack pointer here. I can use this array syntax to refer to the stack pointer of the first CPU, since the breakpoint come back on that CPU, and you see at the top is the return address, and down here we see another pointer, and this pointer is interesting. So the anti-create user process function gets a pointer to an RTL user process parameter structure, and this structure, amongst other things, contains the name of the process that's about to be created. So to take a closer look at the structure, we can use one of the really cool features of Rekall. So essentially Rekall has a profile object. And we talked a lot about the semantic gap during the presentation. And this profile object essentially bridges the semantic gap for us. It contains a lot of information about the guest operating system. Amongst other things, it contains a lot of the structures that the guest operating system is using. And Rekall detects this profile automatically. So I didn't have to tell him we're using Windows 7 64-bit here. He figured this all out by himself. And you can now essentially use tab completion to access the various structures that the guest operating system is using. And you can just cast an arbitrary memory area into that structure. So if I print this newly created variable now, we'll get a list of all the fields in that structure and all the values in that structure. I can even access specific fields in that structure using tab completion and the simple dot syntax. And we see down here is the path of the image that's about to be created. So that's a really helpful feature when you perform kernel analysis or even if you're in user space, because it essentially allows you to navigate through the kernel data structures and take a look at them in Python and interact with them in Python, also in scripts, for instance. And Rekall will go as far as even to try to resolve pointers for you. So if a structure points to another structure, he will automatically try to resolve that structure and give you the correct structure back such that you can use it. So our theory at this point is that this process is about to be created. To verify this, we can take a look at the currently existing processes using the pslist command. So this will list all the processes that currently exist on the virtual machine. And as we can see, this image path is not in the process list yet. That's because the process is about to be created. We just called the anti-create user process function, but it hasn't been created yet. So to figure out when this process is created, we can intercept the return of the anti-create user process function. And to do that, we will take a look at another feature, watch points. So at this point, we will place a watch point at the current stack pointer to figure out when the return address is moved from the stack, since this will then signify the function return. In addition, we will place this watch point just for a single process, not globally as we did for the breakpoints before, even though we could. We have to give a length of this watch point, which we'll just set to 1 byte here, and the type. So whether this is a read access watch point, a write access watch point, or if any access should trigger it, as we are setting it right here. Let's also remove this breakpoint on the anti-create user process function, since we don't need it anymore in this demonstration. 3, sorry. And let's continue. And we see this watch point comes back. And if you take a look at the PS list now, after this watch point returns, we see that this process just has been created and now the image is within the PS list, and we could now go ahead, take a look at the VAT table of this process and keep analyzing, for instance.
So we have one final reveal for you guys. We're going to show you a WannaCry decryptor. Sebastian's going to go ahead and decrypt all of the files on our host machine. And as he's typing, you'll see we're cheating here a little bit. He's simply reverting the snapshot back to the state that we started the demo in. But with that, we just wanted to show you that snapshotting, saving and restoring snapshots on the fly through the Rekall interface is something that we implemented and support as well. So with that, our demo is complete. And I want to leave you with just a very short summary. Hopefully we have been able to convince you that full system analysis is something that is useful and worthwhile. To that end, we showed you rVMI, our debugger on steroids. It is fully isolated from the guest, so we don't rely on any components within the guest to do our analysis. Provides full control and access to the guest VM, and it's completely interactive and scriptable, as we showed you in the demo. As far as we are aware, there's no other tools that fill this niche with the features that we showed you. So we offer this as a open source tool for you to use. We're open for feedback. We really like this to gain some traction. I'll just say a couple of things to the implementation. So we support all the profiles that Rekall supports. We also have a pre-boot profile that we created. Not all of those profiles are as tested and as vetted as the Windows profiles that we generally use. So if you find any bugs, let us know so that we can fix those. Also, Sebastian said it during the presentation, but I'll simply reiterate, Intel only. So the implementation requires an Intel CPU with VMX extensions. Finally, as it exists in the repository right now, it's all source code. So if you're comfortable compiling it yourself, you're clearly welcome to do that. If not, hang tight. It's sort of the first thing on our to-do list. Within the next week, the latest, we hope to get some kind of installer or package up there to make the installation a little bit easier. So with that, the talk is concluded, and take any questions if there are any. Yes?
Semantic layer is so nice. Is it possible to do crash dumps or?
So it's Rekall. So Rekall supports a whole bunch of formats. Crash dumps among them in various formats, raw. I mean, Rekall is a memory forensics tool. Have a look at it. Like I said, it's really powerful, and you can do sort of static memory forensics on all kinds of formats. All right, thank you.
Yes? Oh, sorry.
Excuse me. Do you have a blog about using rVMI?
Sorry?
Do you have a blog about using rVMI?
A blog, not yet. We're preparing a blog post that hopefully comes out next week.
Thank you.